Welcome to our next lesson in the first chapter, second section of our Algebra 2. We are going to continue by talking about sets of numbers. Again, let's go over some vocabulary real quick. Some things that we need to understand is what is the origin. The origin is our starting point. That's what origin means, where we begin. So the starting point of a number line, it's associated with the number 0, no value 0. Unit distance refers how far a number is from 0. And we'll talk about that again when we talk about absolute value of numbers is a unit distance. When we look at our number line, we see that we are starting at 0. We're starting at 0, and if I move 1 unit to the right, I have the number 1, and then 1 unit more. Then I have 2 units to give me 2, and then I do 1 more number to the right. Now I have 3 units to give me the number 3. And I can do the same thing in the left, but counting each unit in the negative direction. Positive numbers are located to the right, while negative numbers are located to the left of 0. So we have various sets of numbers. First number we're going to talk about is the natural numbers. They're called the natural numbers because they're the one that's natural. They're counting. We can count things. So they start with 1 because the lowest value of things we can count is 1. So we start with the number 1, and then we count another thing, and we have the number 2, and then we count another thing, and we have the number 3, and this continues forever. So we use the ellipse to indicate that, and we'll go ahead and we'll put these in brackets. We call this roster form. We'll talk about that again later. Natural numbers usually uses the stylized double stroke n to represent natural numbers. Whole numbers are all the natural numbers and 0. So what we're actually going to do is we're going to take all of these numbers that we had before, so all these numbers here, and we're going to add them into this list. However, what we're going to do is we have to add in the number 0 and 0. So our whole numbers include 0 as well as all of the natural numbers. So we're adding in 0 to our whole numbers. And again, we use the stylized double stroke W to represent our whole numbers. Integers are all the whole numbers and their opposites. See, again, we're building on the previous set, the whole numbers. So again, we can go ahead and grab this. And so we've got all of these numbers. But now what we need to do is we need to add in their opposites. So let's change colors here again. We're going to add in the opposites. Well, 0 is its own opposite, but the opposite of 1 is negative 1. The opposite of 2 is negative 2. Opposite of 3 is negative 3. And we continue in that pattern to build our set. So now we go forever in both directions. These are the integers, represented by a stylized Z. The stylized Z comes from a German word for the integers. Next, as building on top of that, is our rational numbers. And so what we can do is see that it's any real number where any number A over B, where A and B are integers. So we see how it's building on integers. It's building on the set of integers, but now we say, okay, well, what if I take one integer as a numerator and another integer as a denominator, and we make fractions? And so that's where we get our rational numbers. And so there's a lot more values that we could have as our rational numbers, but some examples are, as we could take any two integers and form the rational numbers, is such as 1/2, or 0.5, which is the decimal version of 1/2. I can write it as an integer of A over B. One of the integers could be negative if we wanted, or both of them could be negative. We also have repeating decimals. That's something that's very important. Repeating decimals. So 0.6 repeated is actually, if I take negative, that is the fraction or the decimal equivalent of the fraction 2/3. If I take negative 2/3 and divide it, we get negative 0.6 repeating. Our whole numbers, of course, are included as rational numbers. Any whole number can be written as a fraction by setting the denominator as 1. 0 is a rational number because, again, 0 can be set over 1 and it still equals 0. We can also have fractions with decimals in them because they're complex, but we can always simplify it to something that is not a decimal. And so if I take this fraction and say I multiply the top and the bottom by 10, I'll get an equivalent fraction of 35 over 70, which is, again, two integers as a fraction. So we have rational numbers. Now our next set, irrational numbers, are numbers that are not rational. Okay, there's a couple different places you'll see two slightly different versions, either the stylized P or the stylized uppercase I for irrational. If it's not in this list of rational numbers, it's irrational. So things that we'll see commonly as irrational are radicals of not perfect squares, the square root of 2. Irrational numbers, when you evaluate them in their decimal form, do not repeat, and they do not have any pattern, and they never end. And so square root of 2 falls in that, as well as square root of 3 or the square root of 5. Any non-perfect square will be irrational. Even things that look like they have a pattern, if they don't repeat that pattern at any point, then these are going to be irrational. And so I'm alternating between zeros and ones, but I'm adding another 0 between each new iteration. And so while this pattern continues and I can predict this number and write it, it is considered irrational. Then we also have some commonly used irrational numbers such as pi, which is the ratio of a circle's circumference to its diameter. It's approximated with 3.14. We can keep carrying the decimals out. 3.14159 and so on, but it never has a pattern, never repeats. We also have Euler's number, which is represented with an E, which is approximately 2.71828, and the pattern continues. Now, rational numbers and irrational numbers come together to form the set of numbers called real numbers. So real numbers combines our irrational numbers and our rational numbers. So if it's rational or irrational, it is real. It corresponds to any number on our number line. And we use the double stroke R to represent real numbers. Now, anything that's not real is non-real. The square root of any negative number is how we get, or even the even root of any negative number is where we get our imaginary numbers from. And they're usually denoted with an I for imaginary. We won't be covering non-real numbers until much later in the course, as well as with complex numbers. Complex numbers are combined of real and non-real numbers. So every number is complex, and it goes into some more deeper theorems later down the line. And we'll again talk more about complex numbers much later in chapter 7, I believe. And again, we see we have our number line with our origin, negative numbers and positive numbers. Rational numbers can be placed between. We see the integers here. And so if I have 1/2, that would be placed between 0 and 1. Negative 2/3 would be over here between 0 and negative 1. And we can continue to plot decimals all along this line, as well as fractions and even irrational numbers such as pi, which is right about here. Here's pi, is approximately there. Euler's number, E, is approximately there. We can plot all of these numbers on the number line. So we have this diagram here that represents the real, or the number system, and we can see how these things are nested into each other. And so our natural numbers start all the way at the bottom, and we saw how whole numbers included the natural numbers. So natural numbers were our numbers 1, 2, and 3, and so on. And then our whole numbers include all of those numbers, but we also add 0 into the mix. And then we get to our integers, which include all the whole numbers and the natural numbers, but also the negative counterparts, -1, -2, -3, and so on, containing that pattern. Our rational numbers will add in our fractions, so such as the 1/2 or -2/3, our decimals, -0.5, our repeating decimals, 0.6 repeating. And then our irrational numbers are things that we cannot take the square root of. as well as with our things like pi and Euler's number. Now, there's nothing else in the real number system other than those two categories. So there's nothing that is real that is not irrational or rational. So we can actually kind of shade this in to note that, hey, there's nothing else in this set other than the numbers that we've already included. And the same thing with complex numbers. They're either real or non-real. So there's nothing that goes in this category over here. But our non-real numbers would be values like the square root of -4. Any type of negative root denoted by I. So let's take a look at our examples, and we'll put these in blue. So we want to look to see what number sets do they belong to. So we look at 0. All right, well, 0 is here in our whole numbers. So 0 is a whole number. So we'll write the W, the double strike W. Okay, so it's a whole number. But since it's a whole number, it means it's also an integer. So it falls under the integer category. It's also a rational number. Because it's an integer, that means it's also a rational number. So we can use the Q for the rational numbers. Because it's rational, that means it's also real. You can use the double strike R. 0 is also a real number. And since it's real, that also means that it's complex. So numbers can be in multiple categories as they're nested in each other. The only thing is 0 is not irrational or non-real. 1/3, that's a fraction of integers, so we know that's going to be in the rational numbers, so we've got the Q. But because it's rational, it's also real. And because it's real, it's also complex. -2.5 falls under the rational numbers. So just like we had with 1/3, we've got the rational numbers, the real numbers, and the complex numbers. The square root of 7, I can't take the square root of 7. If I do, I get a non-repeating, non-terminating decimal. So that's an irrational number. And so we can put it in the irrational category. It still makes it real. It's still a real number, and also a complex number nested in that category. 0.66666, that's a repeating value. We've got that here. So it's rational and real and complex. The square root of 16, if I take the square root of 16, that equals 4. Well, 4 is a natural number. So it's natural as well as whole and an integer and rational and real and complex. However, the square root of -16 gives me a non-real number, so that would go in this category, making it non-real as well as complex.